Hey Chemsters, this is Mrs. Vanderlei bringing you another Chemster video. This is again Chapter 6, Section 5 about bond and molecular polarity. This is your part 2. Hopefully it's your part last as well. Okay, so this section is again how to determine if a molecule is polar or non-polar. The previous video we talked about this. We talked about the bonds being polar or non-polar, looking at the electronegativity difference, and we looked at the molecules. We looked at vectors to see if they canceled out or not. So then this section here is applying both of those concepts, okay? So real quick review, a polar bond is an unequal sharing of electrons between two atoms. One molecule or one atom likes it more than the other one, if you will. You look at the electronegativity differences, determine this. And a nonpolar bond is an equal sharing. They almost love it around the same amount. Okay, so the numbers are very similar, the electronegativities. So what about the molecules being polar? Okay, so a polar molecule has this region in 3 dimensions of a partial negative and partial positive charge. We saw that with the vectors. If the vectors do not cancel out, then it's a polar molecule in that respect, okay? It has the 3D region of partial positive, partial negative. A nonpolar molecule has no regions of partial charges, and that can occur because of 2 things. It can be perfectly symmetrical. If the molecule is perfectly symmetrical like we saw before, then the entire molecule is symmetrical, it's nonpolar. Let me show you what I'm talking about. Hang on. This is what I'm talking about here. This molecule is perfectly symmetrical. What happened to these vectors? They cancel each other out. Like the tug-of-wars, they're going nowhere. All right, so this is what I mean by being perfectly symmetrical, all right, that those vectors cancel out. So what about the bond polarity? If the bonds are non-polar, then the entire molecule is non-polar. Let me go back again. You notice right here, there are no vectors. The bonds are totally non-polar. What about down here? Why is this non-polar? Because the atoms are, the bonds themselves are non-polar. And the same thing with the oxygen one that we had here. All right, why is oxygen non-polar? Because the bonds are non-polar, okay? So if the molecule is asymmetrical, what does that mean? Those vectors do not cancel out, okay? And the bonds are polar, then the entire molecule is polar. So for example, water. Here we have water. We have polar bonds, that's why the arrows, and those arrows do not cancel out because they're asymmetrical. Bent is asymmetrical, so I have a net dipole moment. What about over here with NH3, with ammonia? All right, right here, what's going on? The bonds are indeed polar, but they don't cancel each other out, so there's a net vector charge here. What about down here? This is asymmetrical. The vectors do not cancel out, and I have polar bonds. So here makes it a polar molecule. So this section right here is what I want you to get used to doing. I want you to ask yourself these questions, okay? So the number 1 question is, are the bonds polar? Are all the bonds, in a sense, the non-polar? If the answer is yes, you're done. All right, so if the electronegativity difference of the 2 atoms are really close to each other to get 0.0 to 0.4, you're done. All right, so examples from the prior page would be the NH3, the methane, and the nitrogen trichloride. All right, so what if your bonds are polar? All right, then you go over to this side. So then you're asking, is the molecule perfectly symmetrical where the vectors cancel each other out? If the answer is yes, then it is still a non-polar molecule. And here are some examples from before. Okay, the molecule is perfectly symmetrical in each case. The vectors canceled out. So finally, what if the answer is no, it is not symmetrical? Then you have a polar molecule. So again, looking over here, here's chlorine. That wasn't from the one before, but it still works. Here is carbon dioxide. I use that right here. And here's my water, okay, where the vectors don't cancel each other out, making it a polar molecule. Let's go to the next page. All right, so let's fill in this chart, and then we'll label the diagram above with examples, all right? So I've already put some in. We can maybe add a few more. So electronegativity difference of carbon and oxygen. You go ahead and figure that out. What do you get? Well, hopefully you got 1.0. It's 3.5 minus 2.5. So what does that make that bond? Polar or nonpolar? Hopefully polar. And then let's do the Lewis structure. Okay, it looks hopefully familiar. What is its shape? Linear. Is it symmetrical? The answer is yes. All right, and draw dipoles if applicable. Well, do we have any dipoles if it's symmetrical? No, we don't. So does this fit the question we had before? So the first thing are your bonds polar? If they were nonpolar, you're done. But in this case, it's polar. So then what was the next question? Is it symmetrical? Yes. All right. So is the molecule polar? What did we say? No. Let's go back and look again. So in carbon dioxide, are the bonds nonpolar? No, they're not. Is it symmetrical? Yes, it is. It's a nonpolar molecule. Okay. Okay, so what about water? Well, what's 3.5 minus 2.1? 1.4. Polar or nonpolar? Polar. Let's draw it. Here it is. What's the shape of this? Well, hopefully you remember this from what we just completed. It's bent. All right, is it symmetrical? If it is, yes it is, okay? So what do I do now? I would have to draw my arrows. All right, so what's going on here? I have my electronegativities pulling towards oxygen. So I have a net resultant here. So now I need to draw my dipoles. So here I did. Here's where your region of partial positive. Here's your region of partial negative. It's going towards where the vector is. So is this molecule polar? The answer is yes, it is. Okay. What about the next one? Okay. So if I take H2S, all right, here I go, H2S. Well, when I subtract it's 0.4. What does that give me? Nonpolar. You know what? I'm already done. It is not polar. Okay, I don't have to do anything else. The bonds are nonpolar. The whole molecule is going to be nonpolar. Why don't you take a minute out and go through this with NH3. All right, so is this what you got here? Oops, I forgot to put this up here. Here we go. What's bent? Oh, this was bent. Okay, so here we got 0.9, therefore the bonds are polar. Is it symmetrical? The answer is here, no, it's not. So is the molecule polar? Well, yes, it is. This should not be a no. This should be a yes, silly Mrs. Vanderwelle. All right, here, yes, it is polar. Why? Because the bonds are polar and it is not symmetrical. Okay, so what would I draw my dipoles? It'd look a lot like this. I'll even throw this here and put this down here, and that will work out. So if you look at your vectors from the prior page, you'll see that they do shoot to the top there to make it partial negative on the top. All right, let's see what the next part is. So why do we care about this polarity? Well, it describes many unique and physical chemical properties of water resulting from hydrogen bonding. That's our next topic, is why do I call it hydrogen bonding? Water is called the universal solvent. Why is water such an important molecule for this? It's because it's polar. Okay, how do I know it's polar? Because number one, it's bent, meaning it's not symmetrical. It has polar bonds, therefore it's a polar molecule. And water has many, many unique physical and chemical properties. Now let me just show you here. Here is the fact that it's a dipole. Do you see that these two poles I'm bringing in right here? Well, guess what? What happens when I have a negative and a positive charge near each other? Even a partial negative and a partial positive. There's going to be some attraction going on here. All right, so we're going to have attraction going on here. Okay, ooh, hey there, and some attraction going on here. And so what does this mean? The water molecules are attracted to one another. Okay, and what does that do for it? Well, several things. It actually has a pretty high boiling point when you compare it to other low weight molecules. It has a really pretty high surface tension. You saw that on your take-home lab when you counted how many drops of water fit on that penny, didn't you? All right, And finally, this is going to be more like what your lab on Friday is going to be, or their next lab, and some of your take-home labs. Again, the consequence of water being polar is that it is highly soluble. And what we find out is that like dissolves like. Polar molecules dissolve polar molecules. Nonpolar molecules will dissolve nonpolar molecules. So what are some examples? Well, what are two of my polar molecules from above? Hey, let's look up here. There we go. So what's going to dissolve in what? Well, water and ammonia are going to dissolve in each other right here. Okay, yes and yes. So polar dissolves polar. So water dissolves, ammonia. All right. Well, what about nonpolar dissolving nonpolar? Well, that means carbon dioxide will dissolve in H2S. Okay. Let's go down here. And there we go. Water dissolves polar like CO2. What are some other then ideas here? Well, if polar dissolves polar, nonpolar dissolves nonpolar, what about polar and nonpolar together? Well, they don't dissolve in one another. So water dissolves polar, water does not dissolve nonpolar. So if your example of like oil and water, well, we know water is polar. What's oil then going to be? Nonpolar. All right. So will oil dissolve H2S? Yes. Will water dissolve, or sorry, will oil dissolve carbon dioxide? Yes. Okay. That's important, and that's going to be our next lab. Okay. So hang on a second. So what I'd like you to do now is go through these four first examples here, go through them and answer, fill out the chart here. We'll go over them tomorrow, and then we'll fill out the rest of the chart. So I'm going to leave you with this thought, all right? Don't wait to be great. See you soon. Bye-bye.